Alright, geometry, this is the questions from 11.7 that I didn't do in class that you asked about. So you asked for it, so here it is. Alright, in number 18, they tell you this is area 1, this is area 2, and this is area 3. Oh, I missed some measurements, just a second. See, I could just write those in there, I don't have to waste your time in this video. Alright, they tell you this angle is congruent to this angle, so that tells you got some parallels going on here with AIA. They're just trying to get you to notice that, oh, hey, wait a minute, if there's some of this going on with vertical angles, then yes, in fact, we have similar triangles. If these two triangles are similar, and I know something about the ratio of their sides, then I know something about the ratio of their areas. I'm supposed to try to figure out that, the ratio of figure 1 to figure 2 in terms of area for part A, and for part B, I'm supposed to figure out the ratio of 1 to 3. And both these are area ratios, so, and I have sides to deal with, so I think if I deal with sides, I'll know K, and for this I'm going to have to figure out what K squared is. Okay, 1 to 2, these two triangles, if you use this side as the base, then they both have this as their height. So they have the same height to this point from this base. One base is 3, one base is 6, same height. The ratio of bases is the ratio of areas because they have the same height. So I don't have to deal with the k squared business there. It's just straight ahead base ratio since height's the same. All right, then on B, I have to go to area 1 to area 3. Well, this is what I was talking about before with the similarity. These two triangles are similar. The 3 and 1 is like the 6 of the other. The 5 and 1 is like the 10 of the other. So these sides are all double of this. So in this ratio for B, I know that K is 2. I know that the ratio of sides, I mean, I could have figured that out by taking 10 divided by 5, or taking 6 divided by 3. The ratio of sides is 2, so the ratio of areas better be K squared, and K squared is 4. That's why I say the area of ratios. Oh, wait a minute, you know what I just did? I just realized 1 is always the smaller one. I did all these upside down. Give me a second, I'll fix that. Actually, this one was fine, I just had to fix this one. If K is a half, then K squared is a quarter. Okay, here's 23. I'll keep a little running total tally up here, which one I'm on, so you can fast forward through the video if you need to. And first one, I'm supposed to figure out the first part of 23. I'm supposed to find out the ratio of areas here of DEF to ABF. Oh, and they tell me that this big quadrilateral here, is a parallelogram. That's important because parallel lines tell me stuff about angles, which tells me stuff about whether or not triangles are actually similar. DEF, this one up here, and ABF is the big one. I know these triangles are similar because I got these parallels here, so I got AIA here and here, I got angle, angle, so I have similar triangles. I have similar triangles where there's a 4 and there's a 12 as the ratio of sides. I'll make sure I do this right before. Do this right with small over large is the way they have it here. 4 over 12 is sort of the K here. The K is 4 over 12, but that's not what I want. I want to use K squared. Here I can figure out K. It's just a ratio of sides. They have different heights. They have different everything. So, but they're all similar. So I want to use K squared. You know what? This might make it seem better if you look at the static version later. If I tell you that that's where I got that. Okay, good job. Me. All right, great. All right, in part B, you're supposed to do DEF again now with CEB, this thing over here. Well, here I've got similar triangles again because the verticals and the AIAs and all that stuff. So here we got similar triangles again, but here I know that these lengths are double these. No same heights, no same bases, all just straight similarity. So I got to worry about the K versus K squared again thing here. K in this sense, from again small to big, this is half of this in terms of length. So the area is going to be K squared, which now is a quarter. This one's kind of unusual because we're comparing an area of a triangle to the area of a trapezoid. This little triangle here, which we've been comparing on top all along here, this triangle to the sort of trapezoid that it sits on top of. Well, over here we made the comparison between that triangle and ABF. Notice that this trapezoid DEBA is part of that. So, like, this is 1/9 of the area of the whole thing. So this is like 1 part to the big triangle's 9 parts. Well, then think about how many parts this must be of the triangle. This is 1 part of the 9 of the triangle. This must be the other 8 parts of the 9 of the triangle. I think that's the only way to do that. It's like if this were X, this area, let's say this area were X. I know the area of the whole, woo, kind of missed there. The whole triangle has an area that's 9 times bigger. So that must mean that this piece must be the 8x for these things to add up to the 9x. So the ratio of this one to this one is just 1 to 8. That's all that is. That's kind of a weird one compared to some of the other stuff. I think they're just kind of trying to get you to brag to yourself a little bit about, hey, if I know this ratio and I know that ratio and I know this is part of that, then I can get the ratio of the two things inside. It's really not one of the concepts we actually learned this unit. All right, in number 24, we're supposed to find the ratio first of 1 to 3. I think we're supposed to believe this is a trapezoid. Yeah, it says a trapezoid. So I do in fact have similar triangles here. I've got trapezoid, I got parallels, I got verticals, I got all the angles I need to say these are similar. Okay, so if 1 is supposed to be similar to 3, and this is the corresponding side with this, the sides here are in a ratio of 5 to 10, or half. So we've seen that already. If the ratio of sides is half, and we're talking about similar business, then this is going to be k squared, which is 1/4. Okay. In part B, 1 to 2. 1 to 2, that's the type of thing where I've got this one line where these bases are, so that it must have the same, both those triangles have the same height to that point. If that makes sense, the height from that line to this point is the same for both triangle 1 and triangle 2. Yes, this is a height of triangle 2. You kind of have to look at this almost completely upside down, but this is a perfectly good height of number 2. Oh, wait a second. I don't have that. If I had that length and that length, that would be the ratio of sides. That'd be great, or ratio of areas, which would be great. All right, so I don't know what this length is and what this length is. If I knew that, that'd be great. Well, I don't actually know what this length is and this length is, but I do know their ratio. Remember, this little piece here is part of a triangle that's similar to this triangle over here, and that's the side that corresponds to it. So the ratio of this blue, sorry, I should say red to blue, is the same as 5 to 10. Back to the original similar triangles 1 and 3. So I know that red is half of blue. So if red is half of blue and these things have the same height, then this ratio of areas is 1 to 2. Similarly then for 1 to 4, look this way. I've got this height is half of this height. Sorry, I should do different. I guess I could do red, blue again. This red is half of this blue. Whoa, that's not even blue. It's half of this blue because the same thing. Triangle 1 is similar to triangle 3. You know what I could do? I could make it a little bit slight different. 1 with a wave in it is similar to, because I don't want to say they're congruent, is similar to blue with a wave in it for the same reason. They're flipped, they're similar. So the ratio of heights, now triangle 1 and triangle 4 here, triangle 1 and triangle 4 both have this as their height. Yes, this is the height of triangle 4. Triangle 4 could use that as its height and that as its base. But, so the ratios of these areas should be the same as the ratio of these bases, which I know again is a half. Okay, and then 2 to 4. Well, look at this. Ratio of 1 to 2 is half. Ratio of 1 to 4 is half. So in other words, 1 is half of 4, and 1 is half of 2. So guess what? 2 and 4 have to be equal. This is where they are equal. Actually, I just like saying that, but that's just me. If you want a ratio, 1 to 1 is a ratio. Now trapezoid. I want to know, what is 1 of the whole trapezoid? Well, it's half of this. It's half of this. It's a quarter of this. I kind of like what I did last time was saying, okay, let's say the area of this is x. Then the area of this would have to be 2x. The area of this would have to be 2x. Just x is some number. And the area of this would be 4x. Remember, there's a quarter of that. So looking in the grand scheme of things here, I have a total of 9 pieces, 9 parts of area. This is one of the 9. So it is 1/9 of the trapezoid. Cool problem. Okay, in 29, it takes a long time to just know what they're talking about. First, what I drew here was G as the intersection point of the 3 medians of the triangle. Medians were those lines that go from one vertex to the midpoint of another side. But then they start chopping up the triangle a different way. So let me get the medians out of here. Oh, I think I'm going to want to know where G was. So that's where G goes. And the picture's actually not bad, even though I didn't make it in Sketchpad. I made it in... Whoops, that's really bad. I made it with the Promethean software. Okay, so let's get the medians out of here. This is the point that is going through... Sorry, that's the place where the medians intersect. I got a line parallel to CB. Just trying that so it stays parallel, but it's supposed to go through G. So it's a line about like this. Those little tick marks don't mean anything now. Alright, those are the 2 regions the thing goes into. What is the ratio of the areas of these 2 things? Well, they tell you to see some theorem back in chapter 10. It tells you if you were to draw this back in, that this point is 2/3 of the way from A to line CB. So whatever this is, this if you were to chop this up into thirds, that's where G hits on that line. That's a theorem we had in 10.4 that we didn't actually do. So this length is, whoops, I should probably change to the answer color. All right, so that's whatever this is, that's x, this is 2x. Well, this triangle here then is, I don't want to call this EF, AEF, triangle AEF area-wise would then be 2/3 of the area of the big triangle, ABC. Because of course they are similar because this is parallel and all that kind of stuff. I should have said AFE. Anyway, the way I make it correspond here, that make it similar. Anyway, that triangle would be 2/3 of the big one. Oh wait, I'm sorry. That'd be that much of the big one. This is the length, we're talking about area, right? It's that much of the big one, which is actually a ratio of 4:9. So what is the ratio of? Okay, so we're talking about area now. The area of this would be like the area of this whole section. I could say is 4, Q, whatever, and the area of the great big one is actually like 9Q. It's saying what's the ratio of this part to this part? Well, if this part is 9Q, the part in here would then have to be 5Q. So the ratio of this to this would have to be 4:5. Interesting problem. Not very test-like, but very cool. Again, okay, what are they getting at here? All right, they have a triangle here. They say that LK is the altitude, and it's a total of 12. There's some place along here where you can chop this triangle at a point J so that the two areas become equal. Well, we just did in the last problem. We found out whatever this piece was this fraction kind of squared in terms of area, but then I want the ratio of the two parts inside it, this is just a trapezoid. So let me back up a little bit and see what I'm talking about here. Let's call the two areas, or the two sides here, I want to know this in the end of my problem. Let's call this one down here 12 minus x. 12 minus x. I'm trying to get done with these problems before time runs out. Alright, so the ratio of x to 12 minus x squared should be the ratio of triangle to little triangle to big triangle. I'm sorry, not big triangle, trapezoid. No, I'm sorry, little triangle. Just a second. I'm sorry, this is what we talked about. X squared, x to 12. X is to 12, like little area squared is like little area to big area. That's what we did last time. So, and I actually want, what I want this ratio to be is, if this is supposed to be, these two things are supposed to be equal, I want this little triangle up here to be half of the whole thing. So this better be half. Okay, so let's just fix this now. X squared over 144 better be half. So I solved that for x. I found out that x squared should be 72, so that x should be the square root of 72, which reduces very nicely. 72 is 6 times 2. So there we go. Alright, I just spent a whole lot of time working on this one. It's an awesome problem. And I realized we did this in a sketchpad activity. It was called Triangle Within a Triangle. I have about a minute and a half left, and I just took, I don't know, a vacation time trying to figure out how this works. And it's really pretty cool, and I think I got it. But I used Sketchpad myself, and I kind of cheated. And even in the Sketchpad activity, they don't want you to actually prove this. I'll talk you through it. I got about a minute. First of all, I labeled all the different areas with these P's and Q's here. I know that these 3 outer triangles are the same, and I know these 3 little pinwheel type of quadrilaterals have to be the same. And then this thing is different than all the rest of them. I'm trying to find the area of this, how it relates to the rest of the thing. Well, pretty quickly I figure out that if I add up all those, I know it equals the big triangle. And I know that this triangle here from like C to M to A, that has to be 2/3 of the whole triangle, because the way these two things compare, that's like the whole nature of this 2/3 business. So if I talk about how many pieces are in that, and I know that that's equal double one of these, I find out really quickly that the triangle in the middle is equal to the sum of these 3 little outer P areas. The hard part is figuring out the ratio of the Q area, and I put in the 5s and the 1s and the 3s later, the Q area to anything else, really. And I highlighted here I got a red outline triangle here and a blue outline triangle. If you notice, you see how those are twisted. they are actually similar. And since I know they are similar and I have expressions for their areas, I can get the ratios among the pieces of the areas inside. But it is not easy. You do a lot of crazy square root and reciprocal and all that stuff. I've only got 8 seconds to show you, but believe me, it works. It is cool. It is 1/7 the area. See you later.